Hello and welcome. My name is Ambrish Tripathi and I am a Systems and Application Engineer at Texas Instrument. Today I am going to talk about how to power automotive front-end system. This talk is split into three parts, and in this third and final part I will be focusing on automotive pre-boost power supply solution. Here is the agenda of presentation. First, I will cover key requirements related to pre-boost solution. Earlier, in the other two parts, I have already covered the front-end protection part. We have covered the ADAS processor power supply solution as well as infotainment processor solution. Now in this particular part, we'll go into the details of pre-boost solution, where we will consider warm and cold crank condition, and I will also go into the details of lossless bypass operation. As discussed earlier, pre-boost solutions are needed for automotive system to support start-stop, warm and cold crank condition. The plot shown here is of a typical cold crank waveform where input can go down to 3.2 volts and the transition to the low voltage is pretty fast. So what are the three main requirements of a pre-boost system? First, we need to support this low voltage. Second, we need to support the fast input voltage transient. You can see from 11 to 3.2 volt in less than 1 millisecond. And also, lossless bypass operation is preferred when input voltage is greater than the boost program output. That is, when the boost is not switching. And the main challenge is to achieve all this through low-cost implementation. TI has a wide range of solutions to support automotive pre-boost need. LM5122 has the highest voltage range and can support highest output power and has high efficiency because of synchronous rectification. It can easily support the lossless bypass operation because of a high side FET which can independently turn on. But in the lower and the mid wattage cost sensitive application, non-synchronous solutions are very attractive. LM3481 is one of our most popular boost controller that can support input voltage as low as 2.97 volt and is really perfect for most of the pre-boost application. We'll go into the details of pre-boost application using LM3481 as an example. So waveform shown towards your left has a typical Vin transient during cold crank condition. Now the input voltage, which is shown with this green trace, show the transition from 11 volt to 3 volt in less than 1 millisecond, which is very typical of a cold crank condition. An output voltage of 9 volt is needed to be maintained even in the cold crank condition. Now the design toward your right is of 9 volt 2.4 ampere pre-boost design using LM3481. Now the boost output waveform, which is shown with this blue trace, has a dip in the output voltage when you have a fast input voltage transient. You can see initially when the input voltage was higher than the program boost voltage of 9 volt, the boost output voltage was following the input voltage. But when you see this input voltage transient, so the output voltage take a dip before reaching to its final line voltage, and this voltage dip is undesirable and is not liked by many automotive customers. Now how to ensure that you don't see this dip? You would want to see a waveform which is more like from 11 mode goes smoothly to 9 volt without giving you any voltage dip. So basically what we need to do here is to do loop compensation optimization to achieve higher bandwidth, that is higher frequency crossover for boost solution. With the optimization, what we can achieve is up to like 10 kilohertz of crossover at 60 degree of phase margin, at 10 kilohertz of crossover, compared to earlier 2 kilohertz of crossover, which resulted into improvement of boost output voltage performance. You may see towards your right bottom that the boost output now show no voltage dip while fast input voltage transition from 11 volts to 3 volts. Now the bypass operation in boost is preferred to avoid loss when the boost is not switching. In the synchronous LM5122, it is easily achieved through continuous on high side FET, which is powered by the charge pump. So it can have its independent switching because of the charge pump here. But what about the losses in rectifier diode in the cost-effective non-synchronous solution? Remember, LM3481 is a cost-effective non-synchronous boost solution for automotive needs. But is there something we can do to avoid the losses on the rectifier diode when the boost is not operating? Now, how to achieve lossless bypass operation in the case of non-synchronous boost converter? So what is the solution? So the solution is to replace the rectifier diode with a P-FET, a P-channel FET. Now the turn on and turn off of this P-FET can be controlled by the input voltage using a shunt regulator TL431. During the bypass operation, when the input voltage is sufficient and no boost operation is needed, P-FET conducts and avoid losses, and when boost is needed during the cold crank or start-stop application, the body diode of P-FET can act as a rectifying diode because the P-FET is turned off. We have 3 to 4 reference design where we have used LM5122 or LM3481 and have ensured bypass operation. To support our automotive customer design pre-boost application, we have built a large library of power solution optimized for cost, EMC transients at the input. They show proof of concept and are a great vehicle for the customer to look at during their evaluation phase. For more information, you can log on to ti.com/TI designs and go to the specific design. With that, we have reached to the end of this presentation. Thank you for watching.